I moltes gràcies. La següent ponent serà la Marina Martínez amb el títol Black Holes in Different Shapes.
Hi, good morning to everybody. I'm going to continue to talk a little bit about black holes. I hope you, you enjoy it. I don't know how to. Thank you. Okay. Okay, so black holes are objects that are predicted in the theory of general relativity. But an interesting thing is that they are really astrophysical objects. I mean, they exist in nature. They are really hard to observe because they don't radiate and everything goes through the event horizon and nothing comes out. But since they have a huge gravitational field, then we can observe like the stars doing crazy things around an invisible point. So if we look to the center of our galaxy, we can, well, here there's an image where I show the orbits of the stars going crazy around an invisible point. Let me see if I can. Yeah, here would be the point and yeah, the orbits. Okay. But the black holes that I study are not astrophysical ones. They don't exist in space because, yeah, our space is four-dimensional. But they appear in the string theory, because string theory predicts we have more dimensions. So that's why we study them. And also because studying black holes in higher dimensions, we learn about general relativity in 4 dimensions. So it is still useful. So how do we imagine a higher dimensional black hole? I'm going to give you a picture just about the black string because I think it's kind of easy to imagine it. So first of all, imagine a spherical black hole. This is kind of like a planet, but the surface is not strong like a planet. It is kind of an invisible surface. It's called the event horizon. If you go through it, you cannot come out. Okay, so then imagine we add another spatial dimension, a flat one, like this one here. So then we have kind of this ball, and yeah, we just put it through. So we get a black string. This is a 5-dimensional black string. If we do a cut through it, each cut, like this plane here, each circle represents a spherical black hole. This is kind of the idea. If we study this black string and how it behaves, we find out that it is really unstable and that it cannot exist like this in flat 5-dimensional space-time. That means that if we if we perturb its length, its thickness along its length, it goes kind of crazy, and the end state of this instability, it is a localized black hole, like this one here. So how do we fix this? Our way of doing it is putting the black string inside the box. This box, what it makes is that it keeps space-time tight where the box is. I mean, space-time cannot fluctuate where the box is. It is like hard on there. So it is harder for the black string to oscillate and to decay. But if the box is very big, then the black string doesn't feel the box at all, and it still decays. But if we make the box small enough, then the geometry is kind of tight, and the string is stable. So a question that we can ask right now is, let's study this box, and what are the possible things that may exist inside it? Because in physics, we know that the things that happen in nature are the ones that cost the least energy. So if we have a big box, we already know that the black string is unstable, but what do we have inside it? So we have heat. It's called gas of gravitons. Small fluctuations of the gravitational field, and yeah, that would be it. That's the state that we'll have inside the box. If we've made the box small enough, then you can imagine that this gas kind of collapses and forms a black string, and the black string is the state with the optimal energy to exist. So a question that we ask now is there a critical size of the box where both the gas of gravitons and the black string have the same energy? And well, the answer is yes, there is. And this is what I'm looking for right now. And it is a new shape of black hole. It has the shape of a sausage. And it only exists if we put we keep the box at this critical size. But yeah, it is interesting. Thank you very much.